Hello everyone. Today I'll be discussing a critical concept in operating systems, process synchronization. As we know, modern operating systems handle multiple processes running concurrently and ensuring that um, um, these processes work together without conflict is essential for system stability and efficiency. And on our previous two lecture, we learned about all of process management, and now we'll learn process synchronization. So, whether it's handling multiple users accessing a database, coordinating tasks in a multi-threaded application, or managing resources in real-time systems, process synchronization plays a crucial role in preventing issues like race conditions, deadlocks, and data inconsistencies. Okay, now that we have introduced process synchronization, let's begin by defining it. So basically, it is a technique used in operating systems to coordinate the execution of multiple processes that share resources. It ensures that processes operate in a manner that prevents data inconsistency, race conditions, and other concurrency related issues. This means that when multiple processes try to access shared resources, the operating system must ensure that they do so in an orderly and controlled way. Uh, Basically, what we have learned so far in our previous lecture is how process management works, like how a CPU process a system several ways, multiple applications, a lot of things. But now we'll see how, like, um, without proper synchronization, multiple processes could try modify the same data simultaneously, and which can lead to unpredictable results and system errors. Okay, now why we need synchronization? Like, the CPU was doing all the processes using some basic algorithms and all these things, but now why we need a synchronization? um, as we understand the definition, let's now see how or why we need process synchronization. First of all, we need it for proper sequencing of shared resources. Synchronization ensures that processes access shared resources in an orderly manner, avoiding issues like two processes modifying the same data at the same time. Second is it prevents race conditions. Like, race conditions occur when multiple processes try to access and modify shared resources simultaneously, which can lead to inconsistent results. So synchronization prevents such conflicts by enforcing an orderly access. Then it avoids deadlocks and starvation. We have learned about deadlocks and starvation in our previous slides. Now, deadlock mm, deadlock happens when processes are waiting for each other to release resources, causing the system to freeze, and starvation is when a process is perpetually denied access to the resources it needs. Now, synchronization ensures fair resource allocation and prevents these scenarios. Lastly, it ensures data consistency. By controlling access to shared resources, synchronization guarantees that the data remains accurate and consistent throughout the execution of multiple processes. So now that we understand why synchronization is necessary, let's talk about one of the key challenges in process synchronization, which is critical section problem. So, what is a critical section? Well, it is a portion of a program where a process accesses shared resources, such as say, shared memory or variables. If multiple processes enter the critical section at the same time, it can lead to conflicts and data corruption. Second, uh, like goal, ensuring mutual exclusion. So the primary objective of solving the critical section problem is to ensure mutual exclusion, meaning that only one process can be in the critical section at a time. This prevents race conditions and maintains data consistency. For example, um, if you consider a scenario where multiple processes are writing to the same memory location without proper synchronization, one process might overwrite another's data, leading to inconsistent result. Okay. Uh, so here, um, now that we understand the critical section problem, let's discuss the three key requirements that any solution to this problem must satisfy. First of all, mutual exclusion. Only one process should be allowed in the critical section at any given time, and this prevents race conditions and ensures data integrity. Second, if no process is inside the critical section and multiple processes are waiting, one of them must be allowed to proceed. The system should not remain idle when work can be done. Third is bounded waiting. So there should be a limit on how long a process has to wait before getting access to the critical section. This prevents starvation, where a process is indefinitely delayed while others continuously gaining access. Okay, now um, now let's explore some different methods used in operating systems to achieve process synchronization. Uh, we have software-based solutions like these are algorithms that ensure mutual exclusion without relying on specific hardware instructions. Examples are like Peterson's algorithm or Descartes' algorithm. Then second, we can have hardware-based solutions. These solutions rely on special CPU instructions to achieve synchronization efficiently. Um, Examples include test and set and compare and swap operations, these kind of operations. Then third is locks and mutex. We have learned about locks and mutex in our last lecture. So a mutex is a mutual exclusion lock, which is a synchronization primitive that allows only one process to enter the critical section at a time. And locks help prevent multiple processes from modifying shared data simultaneously. Then fourth is semaphores. A semaphore is a synchronization tool that uses counters to control access to shared resources. There are two types of semaphores, binary and counting. Uh, Fifth is monitors. So a monitor is a high-level synchronization construct that provides mutual exclusion and conditional synchronization. It encapsulates shared resources and allows safe access through procedures. Okay, now we'll look. Now I'll explore one of the first one, software-based solution, and we'll look at the first algorithm, Peterson's solution. What is Peterson's solution? It is a software-based algorithm used to achieve mutual exclusion between two processes that need to access a shared resource. It is particularly useful in scenarios where hardware based synchronization methods are unavailable. Now, how does it work? Um, it relies on two shared variables. Flag I indicates if process I wants to enter the critical section, then turn indicates whose turn it is to enter the critical solution. Now, this algorithm ensures that only one process enters the critical section at a time. A process is waiting to enter the critical section will eventually get its turn. No process will have to wait indefinitely. So, why is it important? Uh, this solution is simple but effective in demonstrating how process synchronization can be achieved using only software. However, it is not widely used in modern systems due to its reliance on busy waiting and lack of scalability. Okay, hardware based solutions. Now, here we have two solutions. First is test and set lock TSL, and compare and swap. So, first one, TSL, how it works. A special CPU instruction test and set is used to check and modify a lock variable in one atomic operation. If the lock is free, that means 0, it sets the lock to 1 and grants access. If the lock is already 1, the process must wait. So basically what it does, it has two options, 0 or 1. If it's 0, that means it's free. Then it sets the lock to 1 and grants access. But if the lock is already 1, that means it's busy and the process has to wait. This is how simple it is. Now, it provides mutual exclusion efficiently and it eliminates race conditions, but it can lead to busy waiting, which wastes CPU cycles sometimes. Second, compare and swap. How it works. Now, CAS, compare and swap, is another atomic instruction used in multi-threaded systems. It compares the value of a memory location with an expected value. If they match, it updates the memory with a new value. If they don't match, the process must retry. This is how it works. Now, it is more efficient than TSL in avoiding unnecessary locks, and it is used in modern synchronization mechanisms like lock-free data structures, but it still like it still is under maintenance to performance issues if too many retries occur under heavy contention. Okay, now synchronization using locks. Now that we've covered software and hardware based synchronization methods, let's see one of the most widely used techniques in operating systems, which is locks. We have learned about locks a little bit in our previous slide, but we'll go through it again. So first of all, mutex. A mutex is a synchronization primitive that ensures only one process or thread can access a critical section at a time. Now, a process must acquire the mutex before entering the critical section. Once done, it must release the mutex to allow other processes to enter, which prevents race conditions and allows only one process at a time in the critical section. but it can lead to deadlock if not handled properly. Second is spin locks, busy waiting mechanism. A spin lock is a type of lock where a process keeps checking or spinning in a loop until the lock becomes available. Now, a process continuously checks the lock variable until it's free. Once it's free, it acquires the lock and enters the critical section. Uh, Basically, it avoids context switching overhead, making it useful in multiprocessor systems. Um, um, but some point it wastes like CPU cycles due to busy waiting, so it's not ideal for long wait times. Okay, now we'll look at the semaphore, um, um, which is a synchronization primitive also, which is used to control access to shared resources in a multiprocessing environment. It is an integer variable that is modified using atomic operations to prevent race conditions. So, um, first of all, we have binary semaphore 0 or 1, also known as a murex. It can only have two values. 0 means locked or 1 means unlocked. It is used for mutual exclusion, ensuring only one process can enter the critical section at a time. Um, for example, like controlling access to a printer so that only one process can send a print job at a time. Then counting semaphore. It can have values greater than 1, which allows multiple processes to access resources concurrently. It is used when multiple instances of a resource are available. For example, like managing access to a database connection pool where multiple connections are available for processes. Okay, now that we understand semaphores, let's discuss the two fundamental operations which is used to manage them. First of all is wait and then is signal. Now on wait, it decrements the semaphore. That means the wait operation decreases the semaphore value by 1. So if a is greater than 0, the process is allowed to enter the critical section. And if a is equal to 0, the process is blocked until another process releases the semaphore. Then signal. Signal in this operation, it increments the semaphore. So it increment or increases the semaphore value by 1. So this operation is used when a process exists. Um, um, the process exits the critical section and releases the resource. It allows waiting processes to proceed. For example, if a printer queue with only one printer available is equal to 1, so a process calls wait, setting s equal to 0, meaning the printer is in use. Now another process that tries to print will be blocked because s equal to print. Now once the first process finishes printing and calls signal, setting s equal to 1, another process can use the printer. So this is how it works. Okay, now let's explore a classic synchronization problem, the producer-consumer problem. This problem demonstrates the challenges of coordinating multiple processes accessing a shared resource. Now, what is the producer-consumer problem? In a system, a producer generates data and places it into a shared buffer. A consumer retrieves data from the buffer for processing. Now, what is the challenge? Like uh, ensuring producers and consumers do not interfere with each other while accessing the buffer. This is the challenge. Now, how semaphores help solve it? First of all, the solution involves three semaphores. First of all is empty, full, and murex. On empty, it counts available empty slots in the buffer. So it ensures the producer does not overwrite when the buffer is full. Second is full, like counts occupied slots in the buffer, which ensures the consumer does not read from an empty buffer. And third, murex, which ensures only one process, like producer or consumer, accesses the buffer at a time. So, um, here on the synchronization process, producer we have wait. It waits to check if space is available, then locks access, adds an item to the buffer, unlocks access, signals the consumer. And on the other hand, the consumer waits to check if an item is available, locks access, removes an item from the buffer, unlock access, and signals the producer. Okay, I'll give you this example step by step so that it will be easy for you. Okay, monitor mechanism. What is monitor? So far we've discussed low-level synchronization mechanisms like semaphores and locks. Now we'll explore a high-level synchronization construct monitors. A monitor is a high-level synchronization construct that encapsulates shared variables, procedures for accessing shared variable, synchronization mechanism. So, unlike semaphores, monitors provide a structured approach to process synchronization, making it easier to manage shared resources. So, how does it work? So, a monitor ensures only one process execute within it at a time. So, it uses condition variables to manage process waiting and signaling. And it uses this wait and signal, same two operations. Wait signal, which is the process that calls wait, is put into a waiting queue until another process signals it. Then a process that calls signals wakes up one waiting process. Now, this mechanism provides better abstraction and modularity than semaphores. It reduces the risk of deadlocks compared to using low-level locks manually. And it makes synchronization easier to implement and manage in high-level programming languages like Java, like synchronized methods, blocks, and C++. We have condition variables. These are the things we can use to program those monitors. Okay, now let's explore some of the most well-known synchronization problems that highlight the challenges of process coordination in operating system. First of all, we have bounded buffer problem, which is the producer consumer problem. We have just saw we just saw this in our previous slide. So basically, like a producer generates items and stores them in a fixed size buffer, while a consumer removes item for processing. Now the challenge is to ensuring that the producer doesn't add to a full buffer and the consumer doesn't remove from an empty buffer. And we use the semaphores like empty, full, murex, these functions to synchronize access. Second is readers writers problem. Now the scenario is like multiple processes like readers need to read from a shared resource like a database or something like that, while others like the writers need to update it. Now the challenge is we have to allow multiple readers but ensure that when a writer modifies the data no readers can access it, because otherwise it will mess up. So the solution we can have it like we'll use read write locks or semaphores to manage access. Then third is dining philosopher's problem. um, so the scenario is like five philosophers sit around a table, each needing two chopsticks to eat. There are only five chopsticks shared among them. Now, the challenge is to prevent deadlock, where everyone is waiting indefinitely, and starvation, where some philosophers never get to eat. So, what is the solution for that? So we'll use murex, semaphores or monitors to ensure safe resource allocation in that case. Okay, now let's see one by one. First of all, bounded buffer problem that we saw already, the consumer producer problem. Now we'll go to next one, skip it, and we'll go to next one until we'll see this reader writers problem in detail. So here uh, it involves two types of processes. First of all readers, and second is writers. Now the readers, it processes that only read shared data. Multiple readers can read at the same time. And writers in this function processes that modify like shared data. Only one writer should modify at a time. Then what is the challenge? Challenge to allow multiple readers to access the resource simultaneously, and then also ensure that when a writer is modifying the resource no other process can access it. Now how can we solve it? So synchronization requirement we need here. uh, if no writer is writing, all readers should be allowed to read without restriction. So this is the basic uh, requirement we can have. Then if there is only one writer can write at a time, like a writer must get exclusive access to prevent inconsistent data modification. So only one writer can write at a time. So that will be the second requirement. Third could be like to prevent starvation with priority based scheduling. So first of all, reader priority. If multiple readers are waiting, they should get access before a writer, because there's a lot of people waiting to read. So and a writer will get access to write this one at a time. Now if the writers queue is very long or the writers are waiting for too long, they should get prioritized over new readers. So it depends on the priority. So we can use murex to protect shared data first of all, and then we can use a read count readers to track the number of active readers. Then we can use semaphores like read lock, write lock, these two locks to synchronize access for them. Okay, next is dining philosopher problem, the one I just shared about. Like, so let's learn it in detail. So first of all, like I said, five philosophers sit around a table, alternating between thinking and eating. Let's say to eat, each philosopher needs two chopsticks, shared resources. There are only five chopsticks. So these are the challenges we can have. We can have deadlock, like if every philosopher picks up one chopstick and waits for the second, they all remain stuck indefinitely because they need two at least. So they cannot eat with one chopstick. So five philosopher, if they pick five chopsticks, they will remain waiting in line for indefinitely. Second is starvation. Some philosophers may never get a chance to eat if others keep acquiring resources first. If others philosophers keep eating, then some philosophers may never get the chance to eat. Then concurrency, like ensuring that multiple philosophers can eat without conflicts. Okay, to prevent deadlock and starvation, we use synchronization techniques here. So first of all, semaphore ordering, like it enforces an ordering of resource allocation, like pick up the lower number chopstick first. Then ensures a cycling wait condition does not occur. So if it occur, then it will be like stuck for forever. Then wait for graph analysis, which detects potential deadlocks by tracking which philosophers are waiting for resources. If a cycle is detected, resources are released and reallocated. Next is asymmetric solution, like one philosopher picks up chopstick in reverse order, like right first instead of left, and breaking circular dependency. Okay, now so far we have discussed synchronization within a single system. Now we'll see how synchronization works in distribution system, where multiple processes run on different machines. Like in a distributed system, processes run on separate machines and communicates over a network. Unlike centralized systems, there is no shared memory, making synchronization more complex. So, here are some techniques we can use. Um, First of all, logical clocks we can use. Um, in distributed system, processes use logical clocks um, instead of physical clocks to maintain an event sequence. For example, like Lamport's timestamp. Um, um, it assigns a timestamp to each event to order operations correctly, and it helps resolve issues like causality, violence in event execution. Then second, we can have message passing mechanisms, which like processes communicate via message passing instead of shared variable. So two common approaches we can use: synchronous and asynchronous message passing. On synchronous, the sender waits for the receiver to acknowledge, and on asynchronous, the sender sends the message and continues execution. Okay, now we'll see how can we implement murex in C++ to ensure um, to synchronize access to shared resources. So in C++, we can have a standard library murex which provides built-in support for thread synchronization. So here we can have standard murex mtx, which how we can declare a murex, and then we can have mtx.log. We can log the murex using this function. Third, like critical section, which is we can have mtx.unlock to unlock the mutex. Now how we can use this in a complete code, I will provide the code for you, don't worry, and so that you can have a look how it works. So first of all, like I said, the first line declares the murex, then the second one logs the murex before entering the critical section, and then we have the critical section, which is protected code that only one thread can execute at a time. Then the fourth one unlocks the murex after execution, allowing other threads to process. So I'll add those codes how, so you will see in which parts of the code we are using these lines to lock. Okay, next is examples in C. uh, so we are using semaphore in C, like uh, here it is often used to limit the number of concurrent threads that can access a resource. So here we have a code using POSIX semaphore. So basically what we are doing, um, we have first line sim t semaphore, which declares a semaphore. Second line sim init and semaphore 0 1. It initializes the semaphore with value 1, binary semaphore. And then sim wait and semaphore decrements the semaphore if it is 0, like if which allows one thread to enter the critical section. Now we have the critical section, the protected region where only one thread can execute. Fifth, we have sim post, where like increment the semaphore, allowing the next thread to proceed. And we can also have another one, like sim destroy, which can cleans up the semaphore after execution. So I will also provide this code, so you can have a look. Okay, now in Java, how Java handles synchronization using the synchronized keyword. So the synchronized keyword here is the thread synchronization, which is a built-in support from Java. um, it ensures that only one thread at a time can access a critical section of code. So basically the synchronized this block ensures mutual exclusion, meaning only one thread can execute this code at a time. So I will also provide this code, so you will have that in hand, but make sure you read those code and understand, because you will get question from these codes. So make sure you understand. If you don't understand, please let me know, but make sure you properly go through all the codes and all the documents or extra resources or examples I'm providing, because I will have like you will have your exam questions from those examples. Okay, now preventing a race condition. So mm, here like we have proper locking mechanism using atomic operations and avoiding shared resource modification. These are the techniques we can have to prevent race conditions. Like we already learned so many uh, um, uh, tools and techniques to prevent race conditions. uh, so practical applications, like um, first of all, like synchronization in database. If we talk about it ensures data consistency when multiple transactions access a database simultaneously. Then threading in OS kernels. So it manages multiple processes and threads efficiently in an operating system. Then cloud computing resource management, which allocates computing resources dynamically in distributed environments. Okay, so As we come to the end of this presentation, let's summarize the key takeaways on process synchronization. Um, First of all, it ensures that multiple processes can execute safely without conflicting over shared resources. Then, like techniques such as murex, semaphores, monitors, and message passing help manage process execution efficiently. Without proper synchronization, systems can face inconsistencies, deadlocks, and performance bottlenecks. So, synchronization plays a vital role in database, operating systems, cloud computing, and multi threaded applications. So, as computing becomes more complex, effective process synchronization is critical for building robust, scalable, and efficient systems. Whether in single core system or distributed environments, implementing the right synchronization techniques ensures smooth and error-free execution. Okay, so that's the end of this lecture. I hope you have I hope you all are understanding this course, the topics, because that's an online asynchronous course, and all of the lectures are recorded, so we don't get the chance to communicate with each other like we usually do in an on-campus lecture or a synchronized lecture. But I will appreciate if you have any question related to this any of these lectures, please email me, or you have a discussion forum in every week, so please make sure you post there if you have any question.